Hello and welcome to our lesson on rational functions. This is going to be from section 8.5 in our text. In this lesson, we're going to be looking at finding the domain of rational functions, the asymptotes, and graphing rational functions. So let's get started. First of all, we need to know how to find vertical asymptotes. And it turns out to find a vertical asymptote, you simply set the denominator equal to 0 and solve. That's also how you find the domain, and the vertical asymptotes are related. Next, how to find horizontal asymptotes. That's a little bit more involved. So what I've done is I've made some notation. You need to know that d sub t represents the degree of the numerator, and d sub b represents the degree of the denominator. So the first case, if d sub t is greater than d sub b, that means if the numerator's degree is bigger than the denominator's, then there is no horizontal asymptote. Part B, if the degree of the top is less than the degree of the bottom, then y equals 0 is the horizontal asymptote. There will be one, and it'll be y equals 0. Part C, if the degree of the top is equal to the degree of the bottom. In this case, the equation y equals n over m is the horizontal asymptote, where n is the lead coefficient of the numerator and m is the lead coefficient of the denominator. And hopefully this will make more sense when we do the examples. Last, slant asymptotes occur if the degree of the top is greater than the degree of the bottom by exactly 1. Okay, and the way that you find a slant asymptote is you have to do long division. And so now that we've got through the introductory definitions and criteria, we need to look at some examples. Okay, first example, problem number 3. The instructions want us to find the domain of the function. So the same way that you would find the vertical asymptotes, to find the domain, we need to find the restrictions. And we know that the denominator of a fraction cannot be 0. So we're going to need to solve this quadratic equation, and the solutions will be the values that x can't be. So the fastest way to solve a quadratic is by factoring. Luckily, this trinomial will factor. If I read the signs, plus at the back means they're both going to be minus in this case. X and x to make x squared. And then numbers that multiply to make 5 that add and make -6 would be -1 and -5. And then I just need to set each factor equal to 0 and solve. So moving the -1 over gives us x equal 1. Moving the -5 over gives us x equal 5. And remember that these are the values that x can't be. So x equal 1 and x equal 5 means that x actually cannot be those. So to write the domain in set notation, we would say the set of all x such that x cannot be 1 or 5. That's the way the domain would look in set notation. If I want to write that in interval notation, remember the domain can be anything all the way to -infinity up to 1, but not including 1. And then we're going to skip over 1 and keep going to 5. X can be anything from 1 to 5, not including those values. or anything bigger than 5 to infinity. So this is the way the domain would look in interval notation, showing that we're going to skip 1 and 5. Anything from minus infinity to infinity, except for these two values. Okay, next example, number 19. The instructions say determine the vertical asymptotes of the graph of the function. And so in this example, I'm going to point out something that you need to watch out for. Remember from our definition, if you want to find the vertical asymptotes, you need to set the denominator equal to 0 and solve. Now that will give you the restrictions as well as the vertical asymptotes. However, if the numerator and denominator have a common factor that will divide out, then that value, that solution from the denominator will not actually produce a vertical asymptote. So let me show you what I'm talking about. X to the third can be written as x times x squared, and you'll see why in just a second I did that. In the denominator, notice that every term has an x. So if I'm going to solve by factoring, the first thing I need to do is factor out the GCF, which is x. And that'll leave me with 2x squared minus x minus 3. And now do you see that the numerator and the denominator have a common factor of x that will divide out? So this x that would have produced a solution to the denominator, since it divided out with a common factor, then this is not going to produce a vertical asymptote. Only this trinomial will produce vertical asymptotes. So we need to set that equal to 0 and solve. Now, if we're going to solve by factoring, I'm going to use the 3R method. And the first R is remove. So we're going to have x squared minus x minus 2 times 3 is 6. And remember, these are going to be values that x can't be. So we're going to say these are not equal to 0. And then we're going to factor the standard trinomial. Read the signs. They're going to be different. X and x. Numbers that multiply to make 6 and subtract to make negative 1. And that would be 2 minus 3 to make negative 1. Now remember, I'm doing the 3R method. So first I remove, now I replace. The 2 that I removed, I now need to replace in front of each x, and then I need to reduce. In the first set of parentheses, I can reduce by 2, leaving me x plus 1. In the second set of parentheses, 2 and 3 won't reduce, and so those come down. And now that that's factored completely, I can set each factor equal to 0 and solve. So for x plus 1 equals 0, moving the 1 over gives me x equal negative 1, and that is our first vertical asymptote. For 2x minus 3 equal to 0, we're going to move the minus 3 over and divide by 2. You have to isolate the x to get your vertical asymptote. And it is important to note that the x equal is part of the asymptote. Since an asymptote is a line, then it has to be represented as an equation. Now, before I leave this problem, by the way, these are the solutions. These are the answers to the question that was asked. Find the vertical asymptotes. I want to prove that these are the only two vertical asymptotes, that this exclusion we did by canceling common factors eliminated this as a vertical asymptote. We're going to prove that with Desmos. So what I have here is I've already typed in the function, and you can see that there's two places where this graph appears to be approaching a vertical line from the left and the right. And if I'm correct, x equal -1 should be the first vertical asymptote here. So I'm going to type in x equal -1, and you're going to see that there's a line there that fits nicely in between the red graph. Notice that the graph is approaching the blue line from both sides, but it'll never touch. That's the special thing about an asymptote, is it is a line that the graph approaches but never touches. Even if I go way up here where it looks like they touch, if I zoom in enough, you're going to see that it's still not touching. It's approaching, but it'll never touch. And then the other asymptote was x equal 3/2. So if I type in x equal 3/2, you'll see that that line again fits nicely in between the red graph. The graph is approaching, but never touching the green line. And so this is how you can use Desmos to verify that you have your vertical asymptotes correct. You type them in with the function. It should fit nicely within the curves there. All right, next example, number 21. This time the instructions ask us to find the horizontal asymptote of the graph of the function. So if we scroll back up to our notes, in order to find the horizontal asymptote, we need to compare the degree of the numerator to the degree of the denominator. So the degree of the numerator is 2, and the degree of the denominator is 2. So here we have the degree of the top equals the degree of the bottom, and that means that the horizontal asymptote is going to be y equals n over m, where n is the lead coefficient of the top and m is the lead coefficient of the bottom, making our horizontal asymptote y equals 3/4. And that's it for that problem. Now, to verify that I'm correct, again, I want to go to Desmos. Here I've already typed in our function, and you can see it over here, and I've put in the asymptote, and when I turn it on, you're going to see that it comes in really close on both sides. The red graph is approaching the purple graph on both sides. And again, the farther I go out, the closer it appears to get. It appears to get to it. But if I zoom in enough, you're going to see that it's still not touching. And so that verifies that what we got for a horizontal asymptote is correct. Next example, number 23. Again, they want us to find the horizontal asymptote of the graph of the function. And again, to find horizontal asymptotes, you have to compare the degree of the numerator to the degree of the denominator. Here, the degree of the top is 2, and the degree of the bottom is 4. So in this case, the degree of the top is less than the degree of the bottom. In that situation, y equals 0 will be the horizontal asymptote. Now, in order to verify that, if I go to Desmos, again, I've already got the function typed in, and I put my horizontal asymptote. When I turn it on, you're going to see that it shows up here, and that the graph approaches on both sides. Do you see as I go out, the graph approaches? Now, I would like to point out that this graph does actually cross the asymptote. It goes above it, and then as it comes on to minus infinity, notice it's getting closer and closer, coming back down. So, horizontal asymptotes can be crossed. Vertical asymptotes can never be crossed, but a horizontal asymptote can sometimes be crossed, and it is still an asymptote because the graph approaches but never touches as you go to infinity. Next example, number 25, we have another function. Here they ask us to find the horizontal asymptotes. So again, we're going to compare the degree of the numerator to the degree of the denominator. And here we see that the degree of the top is greater than the degree of the bottom. Now that implies that there is no horizontal asymptote. But if you notice, the degree of the top is bigger than the degree of the bottom by only 1. So in this case, there would be a slant asymptote, but there is no horizontal asymptote this time. Next example, number 27. In this problem, the instructions say, determine the oblique asymptote of the graph of the function. Now, if they ask you for an oblique asymptote or a slant asymptote, that means the same thing. So, for there to be an oblique asymptote, the degree of the numerator has to exceed the degree of the denominator by exactly 1. So, the degree of the numerator we can see is 2. This x has an exponent of 1. That's the degree of the denominator. And 2 is bigger than 1 by exactly 1. So there will be a slant asymptote. The way that you find that is you have to do long division. All right, so we've set up our long division here. You're going to need to obviously know how to do long division. So what would I multiply x by to make x squared? Well, that would be x, and then I need to distribute. X times x is x squared. X times 3 is 3x. Next, draw the line, change the sign, and then combine. 4 minus 3, that is 1x. The minus 1 comes down, and then we rinse and repeat. What would I multiply x by now to make x? Positive 1. 1 times x is x. 1 times 3 is 3. Draw the line, change the sign, and then combine. And that's going to give me minus 4 as a remainder, which I could care less about. What I'm concerned with is the quotient. The quotient, written as a linear equation, is your slant asymptote. And now I'm going to prove that that is the answer. So if I take this function to Desmos, here I've got it already graphed. I'm going to graph what I think is the slant asymptote. So we got y equals x plus 1. Notice that that line fits nicely within the curve. If I go down here, I can see that the black graph is approaching but never touching. And up here, it's doing the same. So this answer that I came up with is the correct answer, producing the slant asymptote for this graph. Next, number 31, I thought it would be nice to do another oblique slant asymptote. So again, to know if there is an oblique or slant asymptote, the degree of the top has to exceed the degree of the bottom by exactly 1, which 3 is bigger than 2 by exactly 1. So we're going to use long division in order to find our slant asymptote. All right, so here we have our long division set up. Now to crank it out, what would I multiply x squared by to make x cubed? Well, that would be x, and then I need to distribute to all 3 terms. X times x squared is x to the third. X times 2x, that's a plus 2x squared. X times negative 1 is negative x. Then draw the line, change the signs, and then combine. Cancel. Negative 1 and negative 2, that's a negative 3x squared. X plus x is a plus 2x. And the minus 4 comes down. And then we rinse and repeat. What would I multiply x squared by now to make negative 3x? Well, that would be -3. And at this point, you can stop. That will be your slant asymptote. The quotient of the long division, if you make it a linear equation, that is your slant asymptote. And I'm going to continue just for fun. -3 times x squared, -3x squared. -3 times 2 is a -6x. Negative times the negative makes a +3. Draw the line, change the signs, and then combine. Cancel. 8x minus 7. This would be your remainder, which you could care less about. We're looking for the slant asymptote. Now to prove that it's right, we're going to go to Desmos. I already have the function typed in, and now we need to input the equation that we came up with, y equals x minus 3. Y equals x minus 3, and this may not look like the slant asymptote the way this looks. Sometimes you may have to zoom out and adjust your window to see that it actually fits the graph perfectly. Look at this. As I come down to the left, the black graph is approaching my blue asymptote all the way to minus infinity. Remember that I said that it may sometimes cross the graph, but the graph should continue to approach your asymptote as you go to infinity. So this verifies that this answer we came up with is the correct slant asymptote.